Hi, good morning. In this session, we are going to discuss about um, Bernoulli trials and binomial distribution in general. And we'll go through some problems which can be addressed using binomial distribution. And we also calculate the mean and variance of binomial distribution and uh, Bernoulli distribution also. So, if you consider a particular random experiment in which we have only two possible outcomes, or if we come across a random experiment in which we are looking for the occurrence and non-occurrence of a particular event, then so let us uh, let A be an event, and we are checking whether this particular event A is occurred or not. If A is occurred, we call it as a success, and if it is not occurred, then we call it as a failure. Or in terms of random variables, say let us create a random variable, capital X, which takes a value 1 when we have a success, or in other words, the event A occurred, and um, 0 when we have a failure or the event A is not occurred. For example, if we throw a die, if we throw a dice and check whether the event A, which gives an even number turns up, then there is only two possibilities: either an even number turns up, or an even number does not turns up, or an odd number turns up. There are the two possibilities. And if an even number turns up, it is a success, and if an odd number turns up, it is a failure. Or if an even number turns up, then our random variable takes the value 1, and if an odd number turns up, then our random variable x takes the value 0. So this is the kind of uh, random experiments which we are going to discuss. And this kind of a random experiment, which has only two possible outcomes, and um, that can be referred to as success and failure, is known as a Bernoulli trial. It is Bernoulli trial, and this Bernoulli trial, and such an experiment is known as a Bernoulli experiment. And the random variable, which is defined like this, which takes two possible values 0 and 1, is known as a Bernoulli random variable. And if you write down the probability density function of a Bernoulli random variable, say Bernoulli random variable, that f of x can take two values. X can be equal to 1 or x can be equal to 0. And say if the probability of success is p, then probability of failure is equal to, naturally, is equal to 1 minus p. So p is a value in between 0 and 1. So as the value of p varies from 0 to 1, or varies in between 0 and 1, we can have different Bernoulli trials or Bernoulli random experiments. So this is the general form of a Bernoulli random experiment, or the PDF of a Bernoulli random experiment. Now, P is a probability of success, and 1 minus P is the probability of failure. Now, um, we can calculate the mean and variance of this particular random variable. Say if we calculate the mean, or in other words, mu is equal to the expectation of x, is equal to summation for all possible values of x into f of x is equal to summation for all values of x take two values here, x is equal to 1, so 1 with probability p plus 0 with probability 1 minus p. So the outcome is small p. So that is expectation of x. So that's the mean of a Bernoulli random variable, and to find the variance, we start with calculating expectation of x square. Expectation of x square is summation for all possible values of x square into f of x, which is equal to 1 square into p plus 0 square into 1 minus p. So that's equal to again p. Now this is expectation of x square. Then the variance is given by expectation of x square minus expectation of x the whole square, which is equal to expectation of x square is p minus expectation of x is also p, so it is p square. If you take a p outside, then it is p into 1 minus p. So that's expression for the variance of a Bernoulli random variable. Now, we are concentrating on the concept of binomial random variable, and say if we have a Bernoulli trial, a random experiment with two possible outcomes, success and failure, and if you repeat the random experiment say n times, now we can define a new random variable capital X as the number of success in n trials, and let us assume that probability of success is a constant p throughout the n trials or n repetition of the experiment. Now, if we calculate, or if we look at the random variable capital X, then this capital X can take values. We can have 0 success, 1 success, 2 success, etc. We repeat the experiment n times and we can have maximum n number of successes. So that is the possible values of X. Now, if you write down the probability density function of the random variable X, we can calculate it using simple mathematical tricks. Anyway, I just give the probability density function, and that probability density function is ncx p raised x 1 minus p raised n minus x, and this x can take values 0, 1, 2, 3 up to n. And this probability density function is known as a binomial distribution. This is binomial distribution, and the random variable x is known as a binomial random variable. So here we are dealing with a random experiment which has two possible outcomes termed as the success and failure, and we count the number of success in n repetition of such a experiment. Now, what about the mean and variance? Before moving into the concept of mean and variance, we can check whether this satisfy the criteria for a probability density function or not. The first criteria, f of x is positive. So ncx is a combination that is positive. P is a probability, it is positive. P raised x is again positive. 1 minus p. P is a value in between 0 and 1, and for 1 minus p is again positive, so 1 minus p raised n minus x is positive, so the value of f of x is always positive. Then what happens if we sum up for all values of x, f of x, and this is equal to 1. And the procedure is very simple. If we look at the expansion of a plus b the all raised to n, which is our binomial expansion, and this is equal to summation um, nc, say nci a raised I b raised n minus I, and in our case a is equal to p and b is equal to 1 minus p. So from this expression a plus b the whole raised dn is equal to p plus 1 minus p the whole raised dn, p plus 1 minus p the whole raised dn, which is equal to 1 raised dn is equal to 1. So using the binomial expansion we can um, verify that this expression f of x is a probability density function. Now let us calculate the mean and variance of a binomial random variable. Let's start with the calculation of mean. So mean is defined as expectation of x, usually denoted by the letter mu, and that's equal to summation for all values of x into the probability density function f of x, and this is equal to summation. In the case of a binomial random variable, x can vary from 0 to n, x can vary from 0 to n, x into ncx, that ncx can be written as n factorial divided by x factorial into n minus x factorial into p raised the x and 1 minus p raised the n minus x. Now this can be simplified as summation x varies from, when x is equal to 0 all this time will vanish, and so we can write it as x is equal to 1 to n. Here just cancel this x and x factorial, so it gives n factorial divided by x minus 1 factorial into n minus x factorial into p raised dx into 1 minus p raised the n minus x. Now one more step, this is equal to summation x varies from 1 to n. I take an n outside from the numerator so that it becomes n minus 1 factorial divided by x minus 1 factorial into n minus x factorial, and also take a p outside so that this term is p raised to x minus 1, 1 minus p raised to n minus x. Now I'm going to make a substitution as y equal to x minus 1, m equal to n minus. So this expression become np into, I just make this change only in the summation form, summation part, it become m factorial divided by y factorial into n minus x is equal to m minus y. You can cross check it, and p raised y into 1 minus p raised m minus y, and this y varies from, as x varies from 1 to n, y varies from 0 to n minus 1, which is m. Now if you look at this summation, it is np into this summation, it is as same as a binomial distribution probability density function with parameter m and p, and the random variable is y. So this summation is equal to 1, or you can use binomial expansion, which we mentioned earlier, to prove that the sum is equal to 1. So this is equal to 1. So the mean of a binomial random variable is 1. Now to calculate the variance, the expression for variance or the formula for variance is expectation of x square minus expectation of x the all square. That is the variance sigma square. But for a continuous type, for a discrete type random variable, it is not so easy to calculate expectation of x square easily. So we use a clerical trick. We calculate the value of expectation of x into x minus 1 first. This is equal to summation x varies from 0 to n x into x minus 1 into the probability density function, that is n factorial divided by x factorial into n minus x factorial into p raised dx 1 minus p raised n minus x, and this is equal to summation. Here when x is equal to 0, this x become equal to 0 and this term will vanish, and when x is equal to 1, x minus 1 become equal to 0 and this term will vanish. So we just rewrite this sum as x varies from 2 to n factorial divided by x factorial into n minus x factorial into p raised dx 1 minus p raised n minus x. And now, as in the previous case, I'm just going to take n into n minus 1 outside from this n factorial and a p square outside from p raised x. So what remains is, here we get an n minus 2 factorial, and the denominator we have an x factorial, n minus x factorial, and e to the power. Okay, here one more thing which we have to do here. This x and x factorial will get cancelled, and x minus 1 and x minus 1 in the x factorial will get cancelled, and what remains here, the denominator, here we have an x minus 2 factorial. So this is x minus 2 factorial. And now it is p raised, I take a p square outside, so it is p raised x minus 2 1 minus p raised n minus x. So this is equal to, the terms outside the summation is n into n minus 1 into p square, and it inside the summation, here the value of x varies from 2 to n, but I make a substitution as n minus 2 is equal to m and x minus 2 is equal to y. So this is equal to m factorial divided by y factorial into m minus y factorial into p raised to y 1 minus p raised to m minus y, and the variation in the summation is taken over y, and y can vary from 0 to m minus 2, that is m. And as in the previous case, this summation is equal to 1, and therefore what we have is expectation of x into x minus 1 is equal to n into n minus 1 into p square. But actually what we are going to calculate is expectation of x square. So we expand this expression, it is expectation of x square minus x, and that's equal to n into n minus 1 into p square, and that is, since expectation is a linear operation, it is expectation of x square minus expectation of x is equal to n into n minus 1 into p square, and Now we are looking for expectation of x square, which is equal to n into n minus 1 into p square plus expectation of x. Expectation of x is the mean, that is n into p. And to calculate the variance, sigma square is equal to expectation of x square minus expectation of x, the whole square. And in our case, this is equal to, if we expand this, we have n square p square minus n p square plus np minus expectation of x the whole square. This is equal to, here it will become n square p square, and this here we have an n square p square that will get cancelled, and what we have is np minus np square. We can take this np as a common factor, so it is np into 1 minus p. So that's the variance of a binomial distribution. So this is the variance. And if you are looking for the standard deviation of a binomial random variable, standard deviation is the value of sigma, and that is the square root of n into p into 1 minus p. In some textbooks, the term 1 minus p is written as q, so the variance is npq, and standard deviation is square root of np. So that is the mean and variance of binomial random variable. Now let us solve some problems which can be solved using binomial random variable. Let us solve a problem in which we toss 10 coins simultaneously. So here the problem statement, a toss 10 coins, 10 say fair coins, this experiment, and they are tossed simultaneously, and find the probability that getting at least 7 heads, probability of getting at least 7 heads. So we are looking for the number of heads that turns up. So we have to define the random variable accordingly, and I define the random variable as the number of heads turns up when we toss, or when we toss a coin or 10 coin simultaneously. When we toss 10 fair coins simultaneously. So that's the definition of our random variable. Now, obviously, the random variable x can take values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. These are the possible values which can assume by the random variable x, as we are counting the number of heads that ends up uh, in a 10 tosses of a fair coin. And now, if we write down the probability density function associated with this random variable, actually here we are we have a random experiment of tossing a coin which has two possible outcomes, and turning up a head is termed as a success, and we repeat the same experiment 10 times and count the number of successes. So it is a binomial type random variable, and so here we can write the probability density function. Here f of x is equal to ncx, n is equal to 10 here, since we toss the coin 10 times, n is equal to 10. So 10cx, we assume that the coin is a fair coin. So p is equal to 1 by 2, 1 by 2 raised to x. Then 1 minus 1 by 2 is again 1 by 2, 1 by 2 raised to n minus x, or 10 minus x clearly. And x can take values 0, 1, 2, 3 up to 10. But here we can simplify one more step, as it is 10cx, 1 by 2 raised to x into 1 by 2 raised to 10 minus x, and this x can vary from 0, 1, 2, 3 up to 10. Now the simplification is possible only because the coin is a fair coin, and anyway we are looking for the probability that number of heads we are looking for the probability that we get at least 7 heads. So 7 or more heads. We are looking for the probability that we have 7 or more heads. That is probability that x is equal to 7 plus probability that x is equal to 8 plus probability that x is equal to 9 plus the probability that x is equal to 10. Because all these events are mutually exclusive, we can find the probability as directly as a sum. And this is equal to, if we substitute the value x is equal to 7 in our probability density function, it is 10c7 1 by 2 raised to 10 plus 10c8 1 by 2 raised to 10 plus 10c9 1 by 2 raised to 10 plus 10c10 1 by 2 raised to 10. So this 1 by 2 to the power 10 can be taken as a common factor, and the remaining terms you may use it is better to use calculators, and anyway the values are 120 plus 45 plus 10 plus 1, and the required probability is 0.171875. So this is the required probability of getting at least 7 heads while we throw a fair coin 10 times. Okay. Now let's have another problem. Here we have a random variable x, which is said to be a binomial random variable. So x is a binomial random variable, and it is given that the variable x has mean and variance 16 and 8 respectively. Mean of x is 16 and variance is 8. Now what we have to find is probability that x is equal to 0 and probability that x is equal to 1. That is what we have to calculate. So we have a random variable which is a binomial random variable, and it's given that mean is equal to 16 and variance is equal to 8. So that means for a binomial random variable the mean is n into p, and that value is 16, and variance is n into p into 1 minus p, and that value is 8. That's a given test. So from these two expressions, if we divide the variance by mean, or np into 1 minus p divided by np is equal to np into 1 minus p divided by n into p is equal to 8 by 16, or is 1 by 2. This np and np will be cancelled, and what we get is 1 minus p is equal to 1 by 2, and that gives p is equal to we transfer it here, p is equal to 1 by 2. Then since p is equal to 1 by 2, if we substitute p is equal to 1 by 2 in our expression for variance, np is equal to 16. That will give, since p is equal to 1 by 2, n is equal to 16 into 2, that is 32. So our probability density function of a binomial random variable f of x, or some case we write it as b, x, and p, because it contains only two parameters n and p, is equal to here n is equal to 32, 32 cx p raised the x 1 minus p raised the 32 minus x. Okay, anyway, the value of p is also known. P is equal to 1 by 2. So this one can be written as 32cx 1 by 2 raised the x 1 by 2 raised the 32 minus x. So as in the previous case, we can simplify or rewrite it as 32cx 1 by 2 raised the 32, and this x can take values from 0, 1, 2, etc. up to 32. Thus our probability density function of the random variable x. Now we can directly calculate probability that x is equal to 0. That's equal to 1 by 2 raised to 32 into 32 c 0. And the probability that x is equal to 1 is 1 by 2 raised to 32 into 32 c 1. So these are the two required probabilities, and you can just rewrite it as 1 by 2 raised to 32 and find the value using your calculators. And the second one is 32 divided by 2 raised to 32. 32 divided by 2 to the power 32. So this is not 32 divided by 2 to the power 32. So this is how we calculate the probabilities. Now let's have one more problem. So here, in a binomial distribution consisting of 6 independent trials, the probabilities of 1 and 2 success are given. Probability of 1 success, that is equal to 0.28336, and probability of 2 success is 0.0506. So these are given, and what you have to calculate is the parameters of the distribution. That is, we are looking for the values of n and p. These are the parameters of a binomial distribution. Now we have in the question itself, the value of n is given. So n is equal to 6. So we already have the value of n. Now what remains is to find the value of p. And for that, we can use this two identities. Probability that x is equal to 1 and probability that x is equal to 2 are given, and from that expressions we can find the value of p. So since probability that x is equal to 1 is 0.28336, we can write so the probability density function is ncx, that is 6cx p raised x 1 minus p raised 6 minus x can take values 0, 1, 2, 3 up to 6, and probability that x is equal to 1 is given by 6 is 6c 1 p raised to 1 1 minus p raised to 6 minus 1, and this value is equal to as per the problem it is 0.28336. So this NC1 or 631 is nothing but 6, so it is 6p into 1 minus p raised to 5 is equal to 0.28336. So it's a fifth degree equation in P, or fifth or sixth degree equation in P, and solving that equation is not so simple. Anyhow, we have one more information, that is probability that x is equal to 2 is 6c2 p raised 2 1 minus p raised 6 minus 2, that is 4, and that's equal to, that's the value is equal to 0.0506. Now that's equal to 6c2 is 6 into 5 divided by 1 into 2, that's equal to 30 by 2 is equal to 15. 15p square into 1 minus p the all raised to 4 is equal to 0.0506. So this is our equation number 1, and then it be equation number 2. And if you take the ratio between equation number 1 and equation number 2, then what we get is 15p square 1 minus p raised 4 divided by 6p into 1 minus p raised to 5 is equal to point. Okay, we can take this larger quantity in the numerator. So I think 6p into 1 minus p raised to 5 divided by 15p square into 1 minus p raised to 4 is equal to 0.28336 divided by 0.0506. Now this ratio is equal to, this is 28 by 5, that gives here we can make some simplification. This p and 1p here get cancelled, 1 minus p raised to 5 and this p get cancelled, and so 6 by 15 into 1 minus p is equal to 28 divided by 5. Here we have a p, so divided by p is equal to 28 divided by 5, or 1 minus p divided by p is equal to 28 into 15 divided by 5 into 6. So it is that means 1 minus p is equal to 14p, or if we transform this p here, 1 is equal to 15p, or p is equal to here 1 minus p is equal to 14. So if you transform it into left hand side, it is 14p is equal to 1, or p is equal to 1 by 50. So the binomial distribution is f of x is equal to 6cx, uh, t is equal to 1 by 15 p raised x. 1 minus p is 14 by 15, 1 minus 1 by 15. All raised 6 minus x, where this x varies from 1 to up to 6, 0, 1, 2, 3 up to 6, the variation of x. So this is the required probability density function of the random variable capital X. So that is how we deal with the concept of binomial random variable. And the problem with binomial random variable is the calculation of probabilities become too difficult when the number of repetition of binary knowledge trials become too large. That is, if we are looking for the number of success out of 100 trials of a Bernoulli, 100 repetition of a Bernoulli trial, then the calculation involved terms like 100 C 500 or 100 C 400. That kind of combinations are involved in the expression, and in that case the calculation become too complicated. In that case, we approximate this binomial random variable to a Poisson random variable, and in our next session, we are going to discuss about an important kind of random variable, which is known as the Poisson random variable, and the distribution is Poisson distribution. And this particular distribution is has a lot of application in communication problems, queuing theory problems, etc. Anyhow, in our next section, we will go through the concept of Poisson distribution, and we can approximate a binomial random variable to a Poisson random variable, uh, and that make the calculation much simple. And anyway, for the time being, we stop here. Thank you.